students? Am I audible?
Yes, sir.
Yes, sir.
Okay. In today's lecture, we will be continuing our discussion regarding the boundary conditions. Okay. So till now we have discussed regarding the dialectic boundary condition. Okay, so we have discussed about the dielectric boundary conditions, and then conductor dielectric boundary condition also. Okay, so in the last class we have discussed about the dielectric conductor boundary condition. Now one more boundary condition, or one more case is left out, okay, which is the conductor to free space boundary condition. So this conductor to free space boundary condition is very similar to the previous case of dielectric to conductor boundary conditions. Okay, because conductor dielectric is very similar to conductor free space. How? Because in the first medium, in this conductor dielectric case, the first medium is the dielectric, okay, dielectric medium, and the second medium is the conductor. And as we have discussed that the electric field intensity of the conductor medium is 0. Okay, so the first, or you can say the first medium was a dielectric medium, and second medium is a conductor with electric field intensity 0. Now, since electric field intensity is 0, so the electric flux density D is also 0, that we have already discussed in the last class. So the only electric field and electric flux density exist in the dielectric medium. Okay, so there are tangential component and normal component of both electric field and the electric flux density. Now the case is that over here the relationship between electric field intensity and the electric flux density is that D is equals to mu E, that we all know, and mu is the permittivity of the medium. Now which can be written like this: mu is equals to mu naught mu r. Okay, this is known to you because this is already you have studied in a physics level. The epsilon is nothing but, sorry, not mu, epsilon. So epsilon is nothing but epsilon naught epsilon r. So epsilon is the permittivity of the medium, so which is equals to absolute permittivity multiplied by the relative permittivity. Okay, now absolute permittivity is having the value constant value, we all know. Okay, it is having some constant value. It is a constant because this constant is absolute permittivity, means it is the permittivity of free space. Okay, free space actually. Okay, so air or free space, whatever. Okay, they are almost equal. Now relative permittivity means the permittivity of the dielectric medium with respect to free space. So it can be any whole number, say 2, 3, 4, whatever. So it is always greater than 1 for any dielectric. If it is equals to 1, that means that mu is equals to mu naught into 1. So mu is equals to mu naught. So that means it is actually free space. So in free space, the mu r value is 1. Okay, and in dielectric medium, the mu r value is always greater than 1. So free space is nothing but similar to dielectric, only this mu will be equals to mu naught. Mu r is not there. So whatever case we have seen for this particular dielectric to conductor boundary condition, that conditions that the tangential component is 0, okay, and normal component is equals to the normal component of the electric flux density is equals to the surface charge density. Okay, so that we have seen. So in conductor free space we will get the same relationship. Okay, so relationship is same here also. The tangential component will be 0. Why? Because you can see this condition is similar to the dielectric to conductor condition. Okay, because only difference is that mu will be equals to mu naught into 1. Okay, so same thing, whatever things we have derived, okay, we will take basically if you take a circuit like this, okay, this is delta W, this is delta H, and if you take a Gaussian surface, okay, so whatever, and this is suppose area is delta S, so whatever means calculation you do, okay, on these particular mediums, okay, same thing you will get, same thing. The thing which we got for conductor to dielectric, you will get the same thing for conductor to free space. Only changes you will make that epsilon will be equals to epsilon naught. Okay, for this case, and in the previous case it was epsilon equals to epsilon naught into epsilon r. So epsilon r value is missing. That is why here also the tangential component will be 0. Okay, that is why the tangential component of electric field intensity is 0. So the tangential component of electric flux density will also be 0. Okay. And normal component, if you can see normal component relationship, we have seen that normal component of electric flux density was equals to the surface charge density. Okay, and okay, so D, so similarly if D is equals to rho s, so E will be equals to rho s by epsilon. So En is equals to rho s by epsilon naught epsilon r. Okay, in this case, see Dn, if you see Dn epsilon naught epsilon r, over here only epsilon naught. So here En is equals to rho s by epsilon naught. So same equations, only this part is missing. This part is missing. Epsilon r is missing. You can see. That is why too much explanation is not been given, because as you know that epsilon r is 1. So we can conclude the same thing. We conclude that from the previous case. So that is why it is not that critical for understanding. Okay, so this is the case. Okay, so now we have discussed about all the 3 boundary conditions. Number 1 was the dielectric boundary condition. Number 2 was the conductor dielectric boundary condition. Number 3 is the conductor free space boundary condition. Now let us go for some numericals. Okay, because since the explanation part is over, so let us see the application or the numericals related to this particular boundary condition. So how to utilize these boundary conditions? You can see this particular numerical. It is told that 2 extensive homogeneous isotropic dielectric, okay, mediums are there, okay, and they meet at a plane where z equals to 0. Okay, so 2 mediums are there in this way. If I draw, okay, because figure is already there, but it is little bit dark for you to understand. Okay, so I'm just explaining in this way that, once again, okay, so z equals to 0. So let us draw the Cartesian coordinate axis. Okay, so suppose I draw the z axis, okay, like this. I am not drawing the x axis. Okay, okay, so if I draw the x axis, not required, but just drawing the y axis, because x axis over here, this x axis not required in this case. So this is z axis. So this will be positive z, this is negative z, and this is 0. So that means at this point, okay, so this is y, okay, so this is rather y, this is negative y. So at this point z, the origin, that is the 0, means z is 0. Okay, since we are talking about z axis only, because in the question it is told that the two dielectric mediums are there, they meet at a plane of z equals to 0. That means z is 0 over here. So that, which indicates that there are two medium, okay, medium number 1 and medium number 2, two medium, both are of dielectric. Okay, so upper one is one medium with a having a permittivity of, suppose, epsilon r1. So this is one medium, and the lower one is also one medium. So they are meeting at this particular point, okay, where z is 0. So at z is 0, they are meeting at this particular point. So this is the boundary, this is the boundary, this one, z0 is the boundary. So now the medium 1 is having a permittivity of 4, okay, and medium 2 is having a permittivity of 3. So medium 2 is having a permittivity of 3. So two different dielectric mediums are there. Now medium 1 is having a electric field, it is having an electric field of E1. That means over here there is an electric field of E1 somewhere over here, okay, and the E1 value is given in vector, okay, unit is kilovolt per meter, electric field intensity exists for z greater than equals to 0. That means for medium number 1, because over here it is positive, so z greater than equals to 0 will be medium number 1, and in medium number 2 z is less than 0, less than equals to 0, so that means negative z. You have to find E2 for z less than 0. That means you have to find the electric field intensity of the second medium. Now first medium electric field intensity value is given, you have to find the electric field intensity of the second medium. That means it is told that it is, since it is a dielectric medium, so there is some electric field intensity over here. So what is their value? So you have to apply this boundary condition which we have studied for dielectric boundary condition. So what we have studied in dielectric boundary condition is that, first of all, the tangential component of the electric field intensity are equal. The tangential components are equal. First of all, we have to find the tangential component, because we have only been given the electric field intensity E1. So which means that there is one tangential component E1t and one normal component also E1n. Okay. Similarly, for the case of the second medium also, there is some tangential component and one normal component also. Okay. So we only know this value. E1 is known, E1t is not known, E1n is not known. So using the boundary condition, how we will calculate E2? Because E1 is known, E2 you have to find out. But only thing we know that E1 ET1 or E1t is equals to E2t. Whatever, one can be written first in before t. So E1t is equals to E2t. So first of all, we have to know E1t. If we know E1t, then we can write E2t. So how to calculate E1t? From here we will calculate. That is, first of all, concentrate on this particular vector or E. So E is having two components, tangential, normal. So you can see tangential is along the y-axis, normal is along the z-axis. So in this case, you can see this 3 is the tangential component along z-axis. So how can we calculate? What we will do, since unit vector z is the normal to the boundary, that means unit vector z is the normal to the boundary. That means z-axis is normal to the boundary. Okay, so that means normal component is along the z-axis. So what is the unit vector of the z-axis? Unit vector Az is the unit vector of the z-axis. direction of z axis. Okay, so normal component will have the z axis direction. Okay, unit vector az. So to find out, suppose you have a vector, okay, e1n. So you are finding out the normal component. That means what you will do, you will actually extract the normal component from that. So what you will do, you will dot product with the वेक्टर ऑफ द नॉर्मल कंपोनेंट, यूनिट वेक्टर ऑफ द नॉर्मल कंपोनेंट, मतलब कि वेक्टर है जिससे तुमको नॉर्मल कंपोनेंट को एक्सट्रैक्ट करना है. कैसे? क्योंकि यहाँ पर देखो ये टोटल वेक्टर है, इसका टेंजेंशियल कंपोनेंट है, इसका नॉर्मल कंपोनेंट है. तो नॉर्मल कंपोनेंट को एक्सट्रैक्ट करना है तो टोटल वेक्टर को नॉर्मल कंपोनेंट का जो यूनिट वेक्टर है जिस एक्सिस पे जा रहा है उस एक्सिस को मल्टीप्लाई करना है. अब नॉर्मल कंपोनेंट यूनिट वेक्टर को मल्टीप्लाई कर रहे हैं तो नॉर्मल यूनिट वेक्टर मतलब कि जेड एक्सिस का यूनिट वेक्टर, इसलिए जेड एक्सिस का यूनिट वेक्टर से मल्टीप्लाई कर रहे हैं. तो करने से क्या होगा, इसको अगर हम डॉट प्रोडक्ट करेंगे, इफ यू डू द डॉट प्रोडक्ट विद जेड एक्सिस, जेड यूनिट वेक्टर, so this will be 0, this is 0, so only 3 will be remaining. So 3 is the normal component. Okay, so normal component will be written like this: e1n equals to 3 az, that is 3 unit vector, because normal component means it is a vector, so you have to write the vector also. Okay, so 3 unit vector z is the normal component vector. ठीक है. Now similarly for the second medium also, it will be along z axis, so normal component will be e2 dot z, but we don't know the value of e2, so we will not discuss this now. Okay, now what we have achieved, we have achieved this particular statement. This is equation number 1. suppose now what we will do, we will write the second equation, that is total electric field intensity E1 is equals to E1t plus E1n vector wise, isn't it? Vector wise, vector summation, not algebraic summation, vector summation. So the tangential component is equals to, if I write it 1 over here, so tangential component is equals to total vector minus E1n, isn't it? तो total vector क्या है? total vector ये है 5ax minus 2ay plus 3az. ठीक है, उसके साथ इसको सब्ट्रैक्ट करेंगे 3az, तो सब्ट्रैक्ट करने के क्या होगा, 3az कैंसिल हो जाएगा, तो सिर्फ हमारे पास है 5 यूनिट वेक्टर x माइनस 2 यूनिट वेक्टर y. सो दिस इज द टेंजेंशियल कंपोनेंट, तो ये हमको मिल गया. दिस इज इक्वेशन नंबर 3. तो so you can understand how we are calculating how to get the tangential component. I am repeating once again, you have the total vector. Okay, now tangential vector is not calculated directly because in our question z axis is mentioned, so we can see that the normal component is along z axis, so you have to extract the normal component, so which is we are extracting the z component. So total vector is equals to normal plus tangential, so tangential is equals to total vector minus normal. If you subtract, you will get the tangential vector. Now since this is the diagram, okay, now since as we have discussed that tangential component are equal, okay, because tangential component are equal, this is the boundary condition. What we have studied from the boundary condition, that tangential components are equal. So if tangential component of the first medium is 5 unit vector x minus 2 unit vector y, so for the second medium also it will be same. So 5 unit vector x minus 2 unit vector y, same thing, there is no difference, so we can write this. Okay, now so we are getting this conclusion. So suppose this is equation number 4. अभी टेंजेंशियल कंपोनेंट निकल गया, अब नॉर्मल कंपोनेंट को निकालना है, क्योंकि ई जो है E2 जो है E2 का नॉर्मल कंपोनेंट हमको मिल गया. दिस वी हैव अचीव्ड, वी हैव गॉट. नाउ वी हैव टू फाइंड E2 टोटल, सो इसको जानना जरूरी है. सॉरी, देयर इज अ मिस्टेक. Normal component we have not got, we have got the tangential component, so we have got the tangential component. तो इसको हमने निकाला है. अभी नॉर्मल कंपोनेंट को निकालना है, इसको निकाल लेंगे तो अभी हम E2 को निकाल पाएंगे. तो इफ यू कैन रिमेंबर, देयर इज अ रिलेशनशिप बिटवीन नॉर्मल कंपोनेंट आल्सो, बट विद रिस्पेक्ट टू द electric flux density. The electric flux density case is that the second boundary condition is that the normal component of electric flux density are equal. This we know. So two boundary conditions was there. Tangential component of electric field intensity are equal for dielectric case medium, and normal component of electric flux density are equal. So we have applied this particular concept to find out the tangential component of the second medium of electric field. Now you will use this formula. Now what you can, so now our question is you have to find out E2. We don't have to find D2. We have to find E2. So what is the relationship between E2 and D2? Because we know D is equals to epsilon E. Okay, epsilon E. Now D2n equals to D1n. So that means D2n is equals to D1n, which means I am writing here once again because there is a term which is missing. So if you get confused, so that is why I am just showing the term also. Just one step is being jumped. So D2n, D1n. Okay. So D2n means epsilon naught epsilon R2 E2n. Okay. And over here epsilon naught epsilon R1 E1n. Okay. So just cancel these two. तो क्या रहा? Epsilon R2 E2n epsilon R1 E1n. ठीक है. अभी टेंजेंशियल नॉर्मल कंपोनेंट तो पता है, ये भी पता है, ये भी पता है, तो पता क्या नहीं है ये, तो इसको हम निकालेंगे. ये निकल के ये आया कि नॉर्मल कंपोनेंट ऑफ E2 इज 4 यूनिट वेक्टर Z, क्योंकि E1 का था 3 यूनिट वेक्टर Z, E2 का था 4 यूनिट वेक्टर Z. अभी टेंजेंशियल कंपोनेंट तो पहले से पता है, इसके साथ इसको जोड़ दो, हो गया E2 किलोवोल्ट पर मीटर. So you can see it's quite easy because in dielectric we have to focus on these two conditions, boundary conditions. Okay? So that means we can see that if you know the electric field intensity of one medium of one dielectric, another dielectric is at the boundary, connected at the boundary, so you can calculate that electric field intensity also. Very simple. Okay. Now what we will do, the next step, the next part of the question is angles E1 and E2 make with the interface. Now this interface concept we have already discussed in the previous lectures. Okay, if you can remember, I am just showing you once again. Wait, in this particular lecture. So if you can remember these conditions, that in dielectric we have derived that the refraction, angle of refraction. Okay, so you have derived this concept. That means if one medium is like this, medium number 1, medium number 2, so they are projected in this way. So this is D2, this is D1. So it is not always necessary that they will be of the same angle. That means if I show in this particular case, if I show that this E1 is projected like this and E2 is projected like this. So when they meet, suppose when they are meeting, so there will be some angle difference. Okay, the angle is different, so there is some refraction. Okay, so there is some angle refraction. So that refraction we have seen, because in optics we have studied in a school level that when you are projecting any light from one source in water, okay, water is a medium, dielectric medium. Okay, so when the light is coming out from, or you are projecting the light from the air, okay, we are standing beside the one pond, okay, तालाब के बाजू में खड़े हो, swimming pool के, तो you are projecting the light in the water. Okay, so you are standing in outside the water, so that means you are standing, the surrounding environment or dielectric medium is air or free space. Okay, so this is one medium, so you are projecting the light and when it is entering the water, the light is bending because of the refraction. Same thing whenever you will have two dielectrics mediums of different permittivity, okay, absolute relative permittivity. So if they are having separate different relative permittivity, so the electric field intensity which is traveling from medium number 1 at the boundary, when it will enter medium number 2, okay, the angle will change, okay, so angle will change, and so that refraction we have to calculate. So we will use these formulas, okay, that is tan theta 1 by tan theta 2 equals to epsilon r1 by epsilon r2. So using these equations you can get this particular solution, okay, you can solve this, okay. Okay, so in this way it is done, okay, so you can go through this because okay, if I explain it over here, this is quite dark actually, so I will draw from here so that you can understand. So suppose this is medium number 1 as it is told, this is medium number 2, okay. So this is the electric field intensity E1, this is E1, okay, and this is E2. Now the angle with respect to z axis is theta 2, okay, and here the angle with respect to z axis is theta 1. So theta 2 and theta 1 are not equal, they are not equal, okay, so they are not equal, theta 2 and theta 1 are separate. Now they are making another angle with respect to y axis also, that means the boundary, okay. So which means that the total angle is 90 degree, okay, the total angle is 90 degree. So if this is theta 1, this is theta 2, so this will be some angle, say suppose 90 minus theta 2 or alpha 2, suppose this is alpha 2, ठीक है, तो theta 2 और alpha 2 को जोड़ के हम लोग 90 डिग्री हमको मिलेगा. Similarly here this is theta 1, this is alpha 1, such that theta 1 plus alpha 1 will give you 90 degree. Now this is the normal component E1n, this is the tangential component E1t. Similarly यहाँ पर भी है E2n, ठीक है. यहाँ पर है E2t, यह है E2n. Now since हाँ, तो थीटा 1 और अल्फा 1 मतलब के 90 जोड़ के, सो अल्फा 1 विल बी 90 माइनस थीटा 1 एंड अल्फा 2 विल बी 90 माइनस थीटा 2. सो E1 इज नोन टू अस, सो E1t क्या होगा, E1t मतलब टेंजेंशियल कंपोनेंट का एक्चुअल मैग्नीट्यूड क्या है, ये जो वैल्यू है ये तो पता चल गया कि E है 3 है, तो इसका क्या वैल्यू है, इसका वैल्यू है क्योंकि टेंजेंशियल कंपोनेंट अगर ये है, ये टेंजेंशियल कंपोनेंट है, ये is a tangential component. So what is the magnitude? Magnitude will be root over of 5 square plus 2 square, okay. So it is root over 29, ठीक है. अब tan theta 1 is equals to ratio of E1t by E2t, E1n, इसको रेशियो करके ये मिल रहा है, ठीक है. तो ये निकल गया थीटा 1, और थीटा 1 अगर ये है तो अल्फा 1 निकल जाएगा, सिमिलरली बाकी ये भी निकल जाएगा. तो रिफ्रैक्शन का भी आंसर हमको मिल जाएगा. सिमिलरली सेकेंड मीडियम का भी सेम प्रोसीड्योर है, ओके, सेम प्रोसीड्योर हैव टू फॉलो एंड यू विल गेट द सॉल्यूशन, ठीक है. सो यूजिंग दैट कंडीशन यू विल गेट दिस. नाउ फाइंड आउट द एनर्जी डेंसिटीज इन जूल पर मीटर क्यूब इन बोथ द डाइलेक्ट्रिक्स. एनर्जी डेंसिटीज, दैट मीन्स एनर्जी डेंसिटी मीन्स, ये भी हम लोगों ने डिस्कस किया था कि W इज इक्वल्स टू हाफ ऑफ एप्सिलॉन E स्क्वायर, ओके, तो एनर्जी डेंसिटी दोनों मीडियम का E1 मीडियम 1 मीडियम 2, वी विल यूज अ फॉर्मूला, जस्ट यूज अ फॉर्मूला। वेक्टर को हम क्या करेंगे, वेक्टर जो मॉड है ना, मॉड, तो वी विल टेक दी रूट ओवर ऑफ 5 स्क्वायर प्लस 2 स्क्वायर प्लस 3 स्क्वायर। यहाँ पर 5 स्क्वायर प्लस 2 स्क्वायर प्लस 4 स्क्वायर, बिकॉज टेंजेंशियल कंपोनेंट सेम है, नॉर्मल कंपोनेंट डिफरेंट है, विल गेट द सॉल्यूशन। और लास्ट पार्ट था एनर्जी विद इन अ क्यूब ऑफ 2 मीटर सेंटर्ड एट दिस पॉइंट 3 4 -5। मतलब एक क्यूब है 3 डायमेंशन में, देयर इज अ क्यूब, ओके, एंड द क्यूब इज placed in such a way inside this particular medium, the center point of the cube is this. So what will be the energy inside the cube of side 2 meter length, each side 2 meter length, cube matlab all the sides will be equal, okay, okay, so you have to find out that energy. So not too much difficult because energy ये हमने पढ़ा था, ठीक है, इफ यू कैन रिमेंबर, और नॉट इन दिस पीपीटी, द अदर पीपीटी, ठीक है, ये वाला हमने पढ़ा था कि एक छोटा एनर्जी जब होता है तो वी विल यूज दी वॉल्यूम इंटीग्रल फॉर दी ऑल द सर्फेसेस एंड वी विल कैलकुलेट दी एनर्जी फ्रॉम द टोटल क्यूब। सो व्हाट इज डन, दिस इक्वेशन इज नोन, ओके, दिस इक्वेशन क्यू के यहाँ पर देखो, यह का एक ट्रिक है कि वैल्यू दिया है 4 3 4 -5, -5 मतलब के, -5 मतलब, अच्छा ये वाला थोड़ा सा चेंज करना है क्योंकि आई हैव ओवरलुक्ड दिस पार्ट, दिस इज वेरी इंपॉर्टेंट, वेरी ट्रिकी। यहाँ पर समझना है कि ये जो क्यूब बोला है ना, ये क्यूब, वेयर दिस क्यूब विल लाई, इन द फर्स्ट मीडियम और इन द सेकेंड मीडियम, यू कैन अंडरस्टैंड फ्रॉम दिस पैरामीटर। Z is negative, Z is negative, that means it is lying in the second medium, तो क्यूब जो है वो सेकेंड मीडियम में लाई कर रहा है, तो उसका Z नेगेटिव है, बाकी X और Y पॉजिटिव है, सो इट विल लाई इन दी फर्स्ट क्वाड्रेंट ओवर हियर, ओके, इन दी X ZY plane, or you can say this particular plane, not plane actually because X component is also there, so it will lie over here, and the center is at this point and side is 2 meter. So obviously energy you have to find out, so energy within a cube of 2 meter side centered at this, so energy, which energy, W1 or W2, since it is lying in the second medium we will take W2, okay, and this is the volume integral, because this is not the volume integral, this is per unit volume, you have to see, you have to understand this is per unit volume, okay, that is the energy density. Okay, so you have to find the, we can multiply the volume, we have to find the volume integral. So taking the volume integral, okay, so we will put the values, evaluate, you will get the equation of the energy, which is 4.776 millijoule. Okay, why these values are value of X is from 2 to 4 and Y from 3 to 5 and -6 from -4, because in this case the cube is in the region 2, ठीक है, region 2 में है, तो region 2 जो है वो सेंटर कहाँ पर है, 3 है, सेंटर 3 है, तो मान लो एक क्यूब होता है, ठीक है, एक क्यूब जो होता है इज वेरी मच इंपॉर्टेंट टू अंडरस्टैंड। पहली बात जो है वो -z है, -5 z एक्सिस माइनस है, मतलब कि मीडियम 2 में है, रीजन 2 में। नाउ द सेंटर इज समवेयर ओवर हियर, ओके, सेंटर तो 3 डायमेंशनल सेंटर, so that means the center is dividing it from all respect. Center is 3, सेंटर 3 मतलब x एक्सिस जो होगा, ठीक है, वो 3 है, तो अगर हम लोग इसको प्लॉट कर रहे हैं, ठीक है, ये पॉजिटिव z है, ये नेगेटिव z है, ठीक है, now the center is told to be -5. तो अगर इसका साइड है 2 मीटर, 2 मीटर इज अ साइड एंड सेंटर इज एट -5, तो सेंटर अगर -5 है तो मतलब कि 2 मीटर का जो लेंथ हुआ उसका सेंटर अगर करेंगे तो ऊपर 1 मीटर होगा, नीचे 1 मीटर होगा। तो ऊपर का जो हिस्सा है तो मतलब कि सेंटर, तो मतलब जो हाइट है ये वाला हाइट है, ये वाला हाइट है जेड एक्सिस का, तो ये बीच में जा रहा है तो ये 5 है। तो ऊपर क्या है, ऊपर है -4, नीचे है -3, क्योंकि टोटल है 2 मीटर। सिमिलरली एक्स एक्सिस क्या है, 3 है, तो 3 एक्स एक्सिस मतलब क्या, ये y है, ये x है, तो ये x है, तो ये 3 है, ठीक है। तो ये अगर 3 है तो इसका लंबाई अगर 2 होगा तो शुरू कहाँ से होगा, शुरू होगा 2 से, खत्म होगा 4 से, ठीक है। और y जो है ये वाला हिस्सा, ठीक है, y एक्सिस, तो ये y का लेंथ क्या है, ये 4 है, तो स्टार्ट क्या हो रहा है, y स्टार्ट हो रहा है 3 से, खत्म हो रहा है 5 से। That is why we are taking the range from 2 to 4 for x-axis. This one 2 to 4 because center is at 3. For y-axis we are taking 3 to 5 because center is at 4. Okay, center is at 4. And z is from center 5. Center is -5, so it will take from -4 to -3. Okay, sorry, -6 actually. ये -4 है, ये -6 है, sorry, -6. 4, 5, 6, 3 तो ऊपर है, 4 to 6 और अदर 6 to 4, क्योंकि -4 बड़ा होता है -6 से। That is why we have taken these values and we will integrate. ठीक है, तो इंटीग्रेशन मतलब ये जो हिस्सा है ये तो कांस्टेंट टर्म है, ये कांस्टेंट है, ठीक है। तो इंटीग्रेशन किसका हो रहा है, इसका नहीं हो रहा है, इसका तो वैल्यू हमने ऑलरेडी निकाल चुका है, हम लोग निकल चुके हैं। तो ये दिस dz विल बी इंटीग्रेटेड विद रिस्पेक्ट टू दिस, सो उसका वैल्यू कितना है 2, dy इंटीग्रेशन होगा इसके साथ, वैल्यू क्या होगा 2 ही होगा, dz सॉरी dx होगा, ये पहले वाला dx होगा, dz विल बी अगेन 2, सो 6 वी आर मल्टीप्लाइंग 6, तो इसको 6 के साथ, सॉरी 6 नहीं 8, सॉरी 2 to 4, 4 to 8, 8, so it's very simple, ठीक है। तो बेसिकली इतना भी जरूरी नहीं था क्योंकि वेरी कॉमन सेंस है, क्योंकि अगर क्यूब है, क्यूब अगर 2 मीटर है तो उसका वॉल्यूम क्या होगा, ये कोई इंटीग्रेशन करने की जरूरत है, नो, वॉल्यूम मतलब क्या होगा 8, क्योंकि एक क्यूब इज इक्वल टू वॉल्यूम, हमको तो पता है, स्कूल में पढ़े हो। लेकिन यहाँ पर दिखाना है एज पर द इलेक्ट्रोमैग्नेटिक फील्ड, सो दैट इज व्हाई वी आर शोइंग द इंटीग्रेशन। बेसिकली वी आर जस्ट मल्टीप्लाइंग द वॉल्यूम 8, है ना, क्योंकि अगर 2 मीटर है तो 8 मल्टीप्लाई करने से मिल जाएगा। ओके, सो जस्ट दिस पर्टिकुलर प्रॉब्लम आई एम शोइंग। ओके, सो आई विल डिस्कस द नेक्स्ट प्रॉब्लम इन नेक्स्ट क्लास। If you have any question regarding this problem, you can ask, because this is very tricky question, very important. Okay, so you must go through this. I will share the notes with you in the Google Classroom. You must go through them. Okay. So any questions? If you have any question, you can ask. Is it okay?
Yes, sir.
Okay, fine. Okay, so if you don't have any question, then you may leave then. Okay, so we'll continue the next question in the next lecture. Thank you.